Okay, so welcome, Evan and Ralph, Michelle, and Jacob and Victor and Caesar and Kristen and Lazaro and Nikki and Eduardo. Let's go talk about the quiz. So let me share my desktop. And let's work it out. Okay, so the first question is, consider the surface, x squared plus y squared minus 3z squared equals 1. Convert this equation to cylindrical coordinates and solve for z. Okay. What makes this easy for cylindrical coordinates?
X squared plus y squared.
Yeah, the x squared plus y squared, you just hope for that. Okay, I tried to make this not such a horrible problem. So what we can do is we can change the x squared plus y squared into r squared. So let's do that. And we can write down r squared. And then it was minus 3z squared. Remember, z just stays as z when cylindrical coordinates is equal to 1. Any questions on that? Okay, now I did ask you to convert it and then solve for z, but that's not that hard. I can add 3z squared to both sides and subtract 1, divide by 3 and take a square root. And what I get is that z equals the square root of the fraction, and it's going to be r squared minus 1 over 3. Any questions? Any questions about, and actually technically, let's fix this a little bit. Technically, what should I do to make this true? Yeah, I should put a plus or minus, so let's do that. If that's under basic, yep. I don't think I'd take off a point if you've got plus or minus, but that's something you should think about. Because z can be negative. Certainly, if you look at the original equation, z definitely can be negative. So we should put a plus or minus in there. Any questions at all on part A? Okay, now let's do part B. All right, we look at part B, and we don't quite have, it's not quite as nice and easy as part A, but we can make it nice. If we want to convert to spherical coordinates, what would we like to see that isn't quite there?
X squared plus y squared plus z squared.
Yeah, you hope for x squared plus y squared plus z squared. If you don't have an x squared plus y squared plus z squared, usually you don't want to convert to spherical coordinates, okay? Although it looks like we don't have one, we can have one. And all you have to do is put in a z squared. So I'm just going to copy the original. Will that mean copy? Nope, it won't. So let me go here. Maybe it will actually. There we go. And now I could just adjust it and just add a z squared plus z squared. But if I'm going to add a z squared, I have to subtract a z squared, so then I get a minus 4z squared. Any questions so far? First step. Okay, so now I can take that x squared plus y squared plus z squared, and I can make that r squared. And then you got to remember that z needs to be turned into spherical coordinates also. What is z? So we can write it as rho squared. And then what is z? Yeah, z is rho cosine of phi. So let's go and pop in some letters here. So we have rho squared, and then minus 4 rho squared. times the cosine of phi. And there, wait, is that a phi? I think that's the phi. They look similar. Okay, and that was supposed to equal to 1. Any questions? Any questions so far? Okay, so now it's just algebra. We need to, according to the question, we're supposed to solve for rho. So now we just solve for rho. We can factor a row out. So I'm going to copy it, paste it in, and then adjust. So I can factor out a row squared, and we get rho squared times 1 minus 4. See if it let me do it. Yep. Cosine of phi equals 1. And then finally, we want to solve for rho, so we just divide by 1 minus 4 cosine phi. And let's do that. So we get rho is equal to the square root of a fraction. We got a 1 on the top, and we have a 1 minus 4 cosine squared of phi. And just to make it perfect, I'll also throw a plus or minus in, since we took a square root of both sides. Any questions at all? Any questions at all on question number 1? A little bit messy, but not tricky or anything. It's just messy. Okay, let's take a look at question 2. So consider the point given in spherical coordinates. So we have rho theta phi equals 3 pi over 4 pi over 3. Write the coordinates of this point first in rectangular coordinates and then in cylindrical coordinates. Okay, so what we need to do is we need to write it in rectangular coordinates, and you got to remember that there is a formula for x, y, and z, and we just use that. So first, just so I don't forget, 3 comma pi over 4 comma pi over 3. So what I want to do is I am going to use that equation. So we have x equals, and again, these are important equations. We have rho times, who remembers?
Sine phi times cosine of theta.
Yeah, sine phi times cosine of theta. And now we just plug in. Rho was 3. Sine of pi over 4. There's pi. And cosine of theta was pi over 3. Let me double check if that's actually what it was. Got it backwards. No, theta was first. So theta was pi over 4, and phi was pi over 3. That goes backwards. Okay, and then hopefully you remember what is the sign? What is the sine of pi over 3? Nobody remembers sine of pi over 3? Yeah, sine of pi over 3 is square root of 3 over 2. And what is the cosine of pi over 4?
2 over 2.
Yeah, so we get the square root of 6 over 4 times 3. So we get 3 times the square root. Actually, let's do it this way. So now 3 times the square root of 6 over 4. Any questions so far? Okay, now let's get y. And since it's very similar, I'm just going to copy and paste and then adjust what I need to. So remember y, what's the difference between x and y? Remember x was rho sine phi cosine theta. What's the only difference that y? Yeah, y's got a sine theta instead of a cosine theta. But here's the nice thing. Sine of pi over 4, cosine pi over 4, same thing. So you get the same answer. Any questions on that? Okay, and then finally, let's get z. So let me just copy and paste, and I'll change what I need to change. So z, we still have a rho. The sine of phi becomes cosine of phi, and the cosine theta is gone. So this is cosine of pi over 3. And then times 3. And what is 3 times cosine of pi over 3? This one's actually much prettier. Yeah, that's just 3/2. Okay, I guess I should call that part A. And now let's go to part B. Any questions on converting? And I guess if you want to make it prettier, we can do that. And we can say 3 root 6 over 4, 3/2. Let's put this in. So let's go to fraction. 3 times the square root of 6 over 4, comma, same thing, comma, and z was 3/2. Well, let me do it that way. I gotta do it that way. Okay, and there's my XYZ coordinates, my rectangular coordinates for this point. Any questions at all on the rectangular coordinates? Okay, now I need to go to cylindrical coordinates. The good thing is I know my z already because z is 3/2. That doesn't change because cylindrical coordinates keeps it. So now what we just need to do is we need to find out what this is in cylindrical coordinates. But the nice thing is cylindrical coordinates aren't so bad. We could actually go either way. We can convert from rectangular to cylindrical because we got our rectangular, or you can convert from the spherical to cylindrical, whichever works better for you. And especially once we know our z, that helps. Okay, so if you remember, how does the cylindrical coordinates work from spherical? I think that's a little bit easier if you remember it. What is x is equal to? If you don't remember, well, then we'll do polar. Or we'll do x, y, z. Yeah, x is r cosine theta, but what's r? No, we don't have r yet.
X squared plus y squared, well, the square root of those.
Right, but in terms
together.
of rho, theta, and phi. If you don't remember, then maybe we'll go right from rectangular, because you can always do that. Okay, if you don't remember, let's go right from rectangular. And for rectangular, let's just do that. And we're going to go ahead and I'm just going to just remind so that when I go into the screen to convert, I can have that there. Okay, so now let's figure out what our R theta and Z are. We know Z is just 3/2. R is going to be x squared plus y squared with a square root. Any questions on that? Okay, so that's going to be the square root. And x squared is just going to be 9 times 6 over 16. Any questions on that? Okay, and then y squared is also 9 times 6 over 16, so you get 9 times 6 over 8. And 9 times 6 over 8 is the same as 27 over 4. And we want to take a square root of that. So what we get is the square root of 27 over 4 is 3/4, 3/2 times root 3, or 3 square root of 3. Over 2. And then comma. Theta, we already had from before. Theta was pi over 4. So we just do that. It don't let me. So let's do it this way. Pi over 4. And then Z is 3/2. And I can get rid of the original. And that's part B. Any questions at all on this quiz? Okay, I want to let you know how much calculus do we use on this? Yeah, none. So don't get too used to that, by the way. Even though we're not doing calculus today, everything changes starting next week. So next week is calculus time, and every single day for the rest of the quarter after today, we'll be doing true calculus, where this you call analytic geometry. Not sure if you remember, but do you remember when things have changed? My generation, our class was not called calculus. And you remember what it was called? Again, you don't remember the time, you weren't born yet, but I mentioned it. So when I took the class, they actually didn't call it calculus, they called it calculus and analytic geometry. That was the formal name of the class. And then they decided, I don't know who the they is, to shorten it to calculus. Okay, and that happened before I even got to Tahoe. Any questions at all on this idea? Okay, so now I have a question for you, and we're gonna see if you remember, and I hope you do, because it is the most important thing of all in mathematics. What I want you to do is in the chat box, but listen carefully before you do anything. I want you to type out the definition of a function, but don't hit the enter button. Just type it. So in other words, I don't want anyone else to see it, but I do want you to put it in the chat, in your chat piece without submitting. Okay, and do it to everyone. Don't make it private. Write down what the definition of a function is. So what is the definition of a function? And I want you to put it in the chat box, give you about 30 seconds to do that. And then we'll eventually put it in officially. But right now, I just want you to type it without hitting enter. given that it is the most important thing of all mathematics, I want you to know this. And everyone should know it. Give you a few more seconds. So the definition of a function. Okay, so when I count to 3, I want you to hit the enter button so that you can have it. And I want to make sure that everyone knows the definition of function. It's a really important exercise because you need to know this. 1, 2, 3, hit enter. Okay, so let's see what we got. Okay, function where an input and output is unique, and to each there must be an equation. Okay, turns out you don't have to have an equation, by the way, but you do have to have an input and output. And that's what you get, a relation between sets of data in which one of the sets has no repeating items. And in fact, not just one of the sets, but the range has no repeated items. So the first set can't have repeated, the first set can't, the first set can have repeated, but the second can't. Okay, an input for every output, an expression that has one or more variables. Okay, you actually don't even need variables for a function. It's just you haven't seen a lot of those, but we'll get there next quarter, actually. A range of inputs that correspond to a domain of outputs where there's only one output for each input. Good, good. A relationship between one or more variables. Close, but you don't. But remember, you have to have the uniqueness, and you don't even have to have variables. But this quarter we'll be doing variables. A rule that assigns to every element of a domain set a unique element of a range set. Good, that's the formal definition. And so you're mostly on it. A few of you can deal with it. Okay, so I want to mention that if you have a specific function, you have to define 3 very specific things to fully understand the specific function. What 3 things must you define to understand a specific function? The general words.
The domain, the range, and I can't think of the third one.
The rule.
Oh, okay.
The rule. So you have to see domain and range are 2 biggies, and the third one is the rule, right? So if you just know the domain and the range, it doesn't mean that you know the function, right? If I told you the domain is real numbers, the range is real numbers, do you know what function I'm thinking of?
No, that could be like 99% of all functions.
Yeah, if you did know what function I was thinking of, that means you're a mind reader, and only Proctorio does that, right? So no, you can't know that. So you have to have the rule also. I want to kind of go through his history, our history, by the way. So if you look at, say, last quarter, what were the domain and the range last quarter? And the quarter before, by the way. Very simple. That's a hint.
Yep.
X and Y respectively.
Yeah, but in particular, X is a letter, not a domain. And Y is a letter, not a range.
Oh yeah. What about what Victor's saying? Values on the x-axis and values on the y-axis?
Yeah, even better. Again, without, you don't need letters.
Is it all
Okay,
real numbers?
Real numbers?
there we go. Real numbers for the domain and real numbers for the range. Got it? Okay, so that was last quarter and the quarter before. Now, see how good your memory is? Okay, so now we're going to go more recent memory. What about parametric equations? Our first week of class. What was the domain and the range?
The real numbers to the points R1 to R of n.
Yeah, so the domain was real numbers. And the range, we actually had 2 types. We either had R2 or we had R3. Those were the 2 that we worked on. Do you remember that? So that's what we've already dealt with. We've actually, understood two different kinds of functions now. We have real numbers to real numbers and real numbers to points. Okay, now today, we're going to do a new kind of function, okay, by definition. And let me go to here. And let me give you the big definition. I think I need to be 24th font though. So the definition is the following. A function of two variables is a function. I don't need to define function because I'm hoping you all know what a function is. That is the key word in math in a way, our definition. And let's make this red because that's what is the definition of. Is a function with domain R2. Let's go to there. R2 and range R1. Remember, R1 is just numbers, just real numbers. Sometimes you just say R, but I'm going to emphasize that this is R1, juxtaposing it from R2. So again, to define a function, you need a domain, you need a range, and you need a rule. So there are many examples of functions of two variables, but they all have domain R2, and actually technically domain a subset of R2 and range a subset of R1. Okay. Any questions on the definition? Any questions? Okay, by the way, is an ellipsoid a function of two variables? Yeah, the problem is an ellipsoid. Let me give you an example. Say x squared over 4 plus y squared plus z squared is 1. And if you had to solve for z, and this actually happened today, is you're going to get a plus or minus. Remember that? Remember we had to do some plus or minuses today?
Yeah.
So if you solve for z, you're going to get a plus or minus, and you lose that uniqueness, and functions have to have uniqueness. So an ellipsoid is not an example of a function of two variables. Any questions on that? Okay. So what you have to be able to do is you really almost, for most examples, you're going to have z as a function of x or y. Let me write that down in pretty notation. So z is equal to f of x comma y. And that's what function is going to look like. Any questions on that idea? Okay, you can't have plus or minuses. Those don't count for functions. That's how you usually write these things. Okay, there's lots of examples. Let me just throw an example out. And I'm going to throw it out on purpose for an interesting reason. So there. Let's say we have z equal, let's go, sine of x over y. Okay, is that a function of two variables?
Yes.
Yes, this is a function of two variables. Okay, so we have to do a few things. One is the rule has already been shown because that's what you're staring at. Do you all agree? What's the domain? Is the domain R2? Okay. The hint is look closely. If the domain is R2, that means any numbers X and Y you can plug in and you'll get a number for Z.
No.
we have
No.
restrictions.
Yeah, we have like we can't plug in Y0, for example.
Right. And not even for example, that's what we can't plug in. That's the only thing we can't plug in is something with a Y equals 0. So the domain, that's the domain. Let's make this normal now. Is not just R2, but it's a subset of R2, and that's what you need to be a function. So the domain is, and now it's a set of all xy such that y is not equal to 0. I think here. Is there not equal to that one? There we go. Is not equal to 0. Okay, so it's important to understand the domain. The domain is, you're not looking at numbers anymore now, you're looking at points. And domains can get complicated. This one's not too bad. Okay, now here's a tougher question. Okay, what if I told you by hand to sketch this? How many of you could do that? Right, you could draw your X, Y, Z axes. How many of you can sketch this? What would your strategy be?
I cannot do that.
Okay, I can't do it either, by the way. Okay, at least I can't sketch it the way you've seen before. Okay, so it's just messy. What we looked at earlier this week were things that we could sketch. Okay, at least I could sketch if you practiced a bit. Ellipsoid you can sketch. You gotta like do a little bit of art. But this sucker, good luck. Do you agree? Okay, so we're not going to be able to sketch this using the X, Y, Z axes. It's just too hard. Okay, I'm going to give you another example of a function of two variables that you've all dealt with before, but I probably deal with it more than most of you. And it's not because I teach math, by the way. And that is, if you look at, consider the function where the range is elevation and the domain elevation is the latitude, longitude. Okay, that, I mean, good luck trying to find an equation, right? Okay, so the problem is this is actually hard to draw. You want to draw it on a piece of paper, it's hard to draw, but you can do it. And you do it using a different technique. Anyone know what technique you typically use to draw this example of the function, a real life function?
Computer.
Huh?
I said a computer.
No, even without a computer, we can do it. And so this has been done for hundreds of years, by the way. That's a hint. So forget computers. Yeah, but a special kind of map. Anyone know what the map is called? So let me show you. I got it set up. By the way, I'm about to show you a place you cannot go to. Yeah, you're close, Jesus. It's a topographical map. Topography, that's pretty close. That's what you're. So there's an example. By the way, if you go here, you could get arrested. How come?
It indicates you might be going outside.
You're allowed to go outside, actually. You just can't go here. So
Oh.
don't go here. Yeah, they closed this down. It's $1,000. Actually, they probably wouldn't arrest you, but it's $1,000 fine now to go on this map. But I picked this one because I think everyone could recognize it. Can y'all recognize it?
Yeah.
Okay. There are some places you can go. Actually, Tahoe Mountain you can go, but kind of the main area in between Fallen Leaf Lake and Lake Tahoe, don't even think about, you know, walking there. You can go on Highway 89, which I did last weekend when I took my bike around the lake. But you can't go any of the parks. Just let you know that's not a math thing. That's just you just should know that. They've closed that down at least till the end of the month, and we'll see what happens after. Okay. But more importantly, if you look at this map, hopefully you can all see it. I know it may be hard to see the details, but you can see that first thing is we have your standard XY coordinate system, right? It's just latitude, longitude. But then what do you notice when you look at the details of the map that are all over the place on this map?
It shows elevation.
Yeah, but there's curves. You see the curves? You see the elevation numbers, but more importantly, can you see the curves? Does everyone see them?
Yeah.
Okay. In fact, I can zoom in and that might make it a little easier to see. Let's go to Tahoe Mountain. I think that's the best because that one actually has some real interesting elevation. Okay, so for example, we see this one curve that's 7,000. Okay, so that is a specific curve. What does that mean in terms of the function? So if you stay on that curve, what do you know? Yeah, it means that you have fixed z as a constant. And as soon as you fix z as a constant, then you have a two-variable equation. Not necessarily a function. This is an example. It's definitely not a function. It doesn't pass a vertical line test. But you get a two-variable equation. And that two-variable equation is called a topo line. So again, if you haven't seen this as a hiker like I have, I've known this since I was, younger because I've been hiking forever. But mathematically, what this is you take the dependent variable, you fix it to be a constant, and then you get an equation of x and y, and an equation of x and y without any z is now a curve in the xy plane. Any questions on that? And what you typically do is you draw a bunch of representative topo curves. Any questions on that? Okay, there's another word for topo curve. Anyone know the other word? And it's a math word, the topo line, sorry. So another word for topo line that's a mathematical word, so it doesn't have to be a map of the earth. Heard of it? It's curve, but it's a special kind of curve. It's called a level curve. It's called a level curve. So there's two words you'll see. Level curve is a mathematical word, and topo line is the navigation word. Okay, words, I guess. Any questions on that? Okay, and by the way, if you have a continuous function, actually I should say that because you don't know what a continuous function is yet, so maybe I'll wait until Monday on this one about continuous functions. Yeah, two variables, we don't even know what that is yet, but we'll get there and it'll be what you expect. But that's a topo line, and that's a topo line or a level curve. And it allows you to visualize a function of two variables without having to get real artistic. you can just do it in an XY plane, XY map. Any questions on that? Okay. Doing it by hand is very tedious, but not impossible. Maybe I'll do one by hand. I don't want to do a lot by hand because it just takes too long. So let us sketch the, how about sketch instead of the, how about 4 level curves for, now let's rip one out. Actually, let's just do this one. Z equals sine of X over Y. Any questions on the question? Okay, so what we need to do is we need to pick 4 level curves. Okay, so so now we want to get nice about this. We want to get some good values of Z that kind of show what's going on. Any questions on that idea? Okay, the first thing, I'm not going to pick Z equals 0. How come? Z equals 0 is a little weird and I want to avoid it. Why do I want to avoid Z equals 0? Anyone see it? You have to kind of imagine doing it.
I mean, you'll get Y equals sine of X.
Well, you don't get Y equals sine of X. That's the problem. You don't quite get the origin, but you don't get quite the origin either. Okay, maybe I'll do it because you're not seeing it. So let's start with 0. So 0 equals sine of X over Y. In fact, I can do this.
Can't get the Y value. Or because if we try to solve for it.
You're going to have some issues. So 0 equals sine of X over Y. And the first thing you might want to try and do is multiply by Y. And guess what? You get sine of X equals 0. And if sine of X equals 0, what does that tell you? What's X?
0.
Is that the only thing you could have?
No, you can have 2
No, it
pi.
can also be pi or 2 pi.
Yeah, actually, let's call it K pi. You could have 20 pi. Do you agree?
Yeah.
So X equals K pi.
Watch, you rented what?
Okay, now it's an easy question, but you may not be thinking right. What does X equal K pi look like on the XY plane? Everyone got quiet. It's easy as soon as you think about it.
Isn't it just a point?
It's not a point, it turns out. It's more complicated than that. I heard a line, but what kind of line? It's not any old line.
Vertical
The
line.
x-axis.
It's not the x-axis. Not a horizontal line. It's a bunch of vertical lines. Because if we fit x equals 0, for example, then y could be anything. That's the y-axis. If you let x equal pi, y could be anything, and that is the vertical line at x equals pi. Do you see that? So we're going to get a bunch of vertical lines. Does that make sense?
It's because k is a constant, so x is equaling a constant, right?
Yep. And x equals a constant is a vertical line, and that you learned in beginning algebra. You may not remember it, but it is important. Okay, so we got one. Okay, I guess I should write z equals 0. It's always good to label which level curve you're looking at. And now let's do a copy and paste. And now we're gonna do some that aren't as just lines. All right, I could choose z equals 1 if I want. And that might be interesting, but let's choose something a little more interesting than that. Let's choose z equal we'll do z equals 1. That works. Z equals 1. Then that's a 1. And now all of a sudden, we have a more interesting equation. It's not just a bunch of vertical lines. What does this become? Isn't it y equals sine of x? Any questions on that? Yep, it's going to be a curve. I guess vertical lines are technically curves too, but they're just a little funky. Okay, we got to pick another z. How about z equal 2? Sound good? So then 2 equals sine of x over y, and y equals 1/2. Sine of x. Any questions on that? And let's pick one more. Let's pick, how about 1/2, because that's an interesting one. So then 1/2 equals sine x over y. So y is going to be 2 sine of x. So you'll notice that as long as you stay away from 0, zero's a crazy one. That's why I was a little worried about starting there. These all have something in common. What does every level curve have in common? Yeah, they're all sine curves. And what they have is the amplitude of the sine curve is the reciprocal of z. Is that clear to everyone?
Oh, that's cool.
Yeah, so that's what this is. The amplitude is reciprocal of z. Okay, and again, until you do this, it may not be obvious by looking at the original function z equals sine x over y. It may not be clear that that's what's going on, but it is. So now, let's try it. And this is where it's not going to look great because I'm not the best artist. So, I need okay, so what we get is the nice thing about a lower curves is you don't have to draw the x, y, z axes. You only have to draw x and y, and that's something you've been doing for years and years, right? And what we want to do is we want to draw these guys. Okay. So notice that y is never 0. Just remember that, and that's going to be important when we look at this. So the first thing is I can draw. I'm not going to draw everything, but I'm going to draw some. Let's make it colorful. How about, oops, hit that. There we go. So the first thing is we had x equals 0. Now let's make it colorful. Any questions on that? And then we had x equals pi. Any questions so far? And then let's look at, so that was, that's actually one level curve, even though it looks like 2. We should label those. And you just put the number in. Gonna make it red. Everything should be red here. Wait a minute. That was line color. I think I need to go to, there we go. That's better. And that was a 0 also. Okay, so then what I want to do is I want to draw some of the others. So then remember we had the sine of x. And the sine of x, hopefully you remember. You better know. Looks like this. Okay, again, I'm not a perfect drawer, but you get the idea. It's pretty hard with the mouse. Okay, and that was z equals, let's make it a new color. So that was z equals 1. I don't know why this box is showing up, but it shouldn't. It did something weird, so sorry about that. This was 0. And then we had the 1. Okay. And then if you remember, if you had z equals 2, then the amplitude was 1/2. So let's draw that one. We'll let it be black. Oops. Any questions on that? Again, this is not a perfect sine curve. If I wanted it to be a lot prettier, what would I do?
Desmos.
I like Calplot 3D because it's better for three-dimensional stuff. It does also work, but I like Calplot 3D. And let me show you how to use it because I think it's much easier and much prettier. It does this whole like 3D geometry. You can spin things and all that. That's what you want, but I think Calplot 3D is a little better. So what I'm going to do is let's put in our z. Z is going to be equal to sine x over y. Okay, by the way, that's a three-dimensional picture. Okay, and that's the nice thing about Calplot 3D. You can really see what's going on. But what I can do is I can look at the level curves, and I can do that by clicking on this guy, and I can go to project contours on the XY plane, drop the other one, and then create the plot. And there we go. Any questions? Okay, any questions at all on this? Okay, and you can make it more contours if you want. Instead of 11, you can make it, I don't know, 5, just for fun. Okay, and then you can actually see the contours and the three-dimensional at once. Any questions at all on using technology? And I think you'll agree technology is a hell of a lot better than anything I could do by hand. Okay, and I was not the programmer of this. I know the programmer, but I wasn't the programmer of this. Any questions on dealing with functions of two variables? Any questions? All right, so now we're ready to move up. I'll save and close this guy. So now I want to talk about, what do you think it might mean to be a function of 3 variables? What do you think the difference between a function of 2 variables and a function of 3 variables is going to be? The hint is this is not a trick question. This is supposed to be easy. Yeah, one
just
more
add
letter.
one
I
more
like
letter.
that. One more letter. And in particular, if you look at the definition itself, it's not going to be R2 as the domain. What's going to be the domain?
R1.
R1 or 3? R3. If the domain's R1, that's our good old fashioned, y equals x or y equals x squared or something. That would just be good old fashioned function that you learn in that beginning algebra. So a function of 3 variables, all I have to do is take the other definition and just change the word 2 to a 3, change the number in R2 to R3, and then change the f of xy to f of xyz, but then you probably don't want to have z on the left. Okay? And here's the thing is there's lots of letters you can use. Okay, so this really depends on what you're doing it for. Maybe, let me give you an example. When would this one happen? What do you think capital T might correspond to in the real world?
Function of time.
We almost never use capital T for time. That'd be lowercase. Temperature, yeah, temperature. So if you want to find out the temperature in the room you're at now, and by the way, I don't know what room you're at, and maybe a window's open, which mine would be because it's supposed to be really nice out. And then the temperature is going to change, and it'll be a different temperature near a window than it will be away from the window. And it's going to depend on X, Y, and Z. Does that make sense? So this is an example of a function of 3 variables where the independent variable is just the standard X, Y, Z, and the dependent variable is T for temperature. Okay, sometimes you might have a Z equals f of xy lowercase t. Lowercase t is reserved for what? Yeah, that's time. Okay, so sometimes you'll have something like that. By the way, could you have a function of 4 variables? Okay, yeah, you could. In fact, this morning, this was early morning because I do my exercise watching a physics show or physics MIT lecture, and I was watching a demonstration, and the professor used a function of 4 variables. And what he was doing is he was doing the time-dependent Schrodinger equation. You guys heard of that before?
Say that one more time.
The time-dependent Schrodinger equation. Very important in chemistry and physics. He was actually doing more chemistry, but it's all the same.
Not time dependent.
You've heard of it though, right? Okay, so what that means is that for any point in space-time, so you have your X, Y, Z that you're used to, and you also have the time of day. There's a probability that an electron will be in that location at that time. Have you heard of that before? Okay, I'm not going to go over to it because it's way advanced, but someday you'll get it. Someday you'll learn it, probably, depending on how far you go. And that is a function of 4 variables that's important. Okay, and that's called the time-dependent Schrodinger equation. And in fact, because this kind of brings about what we did last time, what the professor did is he took the time-dependent Schrodinger equation in X, Y, Z, and T and turned it into the spherical coordinate time-dependent Schrodinger equation. Instead of X, Y, Z, T, it was rho, theta, phi, T. And he looked at the probability distribution based on rho, theta, phi, and T. So I want to mention that it may seem like, well, why would you care about 4 dimensions? The answer is yes, you care, because we live, there is such a thing as tomorrow. I know you know that, and yesterday. So time is important. Okay, so you may think we live in 3 dimensions. No, we live in 4 dimensions. What we can feel and see. Because you can go up and down, left, right, forward and backward, and time is happening. We have no control over time, but time is happening. Any questions on that? So I want to mention that these higher dimensions are important, and they come up whenever you're trying to truly understand the real world. It's not some fantasy land. Okay, it's understanding where we are and when we are. Any questions on that? Okay, so what do you think the challenge is going to be when it comes to a function of 3 variables and depicting it?
Restrictions on each variable.
The restrictions, actually, that's not too bad. Challenge is graphing. Yeah, graphing it. Okay. So for example, I'll even do something simple. How about equation? Let's suppose that f of x, y, z was equal to, how about x plus y plus z squared? Okay, you make it even, it may look like this is harder, but that is going to be easier. How about x squared plus y squared plus z squared? How do you graph that? Any ideas? Okay, and the answer, this is hard. Okay, here's what you don't want to do. You don't want to draw 4 coordinates like X, Y, Z, and capital T. You definitely don't want to do that. There's no good way of doing it. You can't make it pretty. It's just not going to work. So there are really 2 choices. One is the analogy. One is the analogy to what we just looked at. And that is, instead of level curves, what do you think we might want to do instead of level curves? Very similar to level curves. The idea, so the idea is that if we fix a number for f, if we take the left-hand side and make it a number, we don't get a curve. What do we get?
Sphere.
Right, but in general, we get a surface. So we're going to be looking at level surfaces. So the analogy to level curves is level surfaces. Okay, now I am definitely not a good enough artist on a computer or even on paper or the board to do good level surfaces, but I'm very good with computers. And hopefully you're at least okay with computers, because that's an important skill to have, okay, for the STEM world. Okay, so what I can do now, I'm going to refresh this just so I can start over. I can just draw them. Okay, how about, and let's add a parametric surface. Oh, sorry, not parametric. I want to go to implicit surface. And I'm going to go x squared plus y squared plus z squared. Let's choose 1 as the first one. And there it is. Okay. And then I could draw another one. So let's add another parametric implicit surface. And we could have x squared plus y squared plus z squared equals, how about 2? Okay, I can't see both of those very well. So one thing I can do is I can adjust the domain. let's make x, y, and z positive, and let's look at the first octant. I don't think I've used that word before, but it's an important word. What do you think first octant means, since I haven't said it before? Okay, so the idea is the analogy of quadrants. Quadrants, if you take the xy plane, it cuts it into 4 pieces. But if you take the x, y, z axes, that cuts the universe into 8 pieces. So that's why you call them octants. Is that clear? So let's make these zeros. And another 0. And let's go. Wait a minute. Didn't I make it a 0? Is it being mean to me? Ah, switched it off. It's just not being nice to me right now. Let's see if I can do it with display format axes panel. Let's try that one. Let's try 0, 0, and 0. See if that works. Much better. Okay, so now I can actually see my level surfaces. Any questions on that? I've only drawn 2. I could draw more if I wanted to. And you get level surfaces out of that. Any questions at all on this example? So level surfaces are a lot harder to draw, by the way. You definitely want a computer to draw level surfaces. And even that, you saw it took me some time. Okay. Any questions on what level surfaces are? Okay, let me do one more example to make sure that you know what's going on. Another question is sketch the domain of f of x, y, z is equal to x, y over z minus x squared minus y squared. All right, how do we go about sketching the domain of xy over z minus x squared minus y squared?
We should figure out when the denominator is 0.
Exactly, and not just figure out, but set the denominator equal to 0. Does that make sense? Okay,
Yeah.
and that won't find the domain. How come?
Because it's not part of the domain.
Yeah, it does the opposite. Instead of finds the domain, we're going to find out what isn't the domain. And usually that's what you need to do. Okay, usually you don't sketch the domain, you sketch what isn't the domain and say everything but that. So now, again, there's a nice little review. We set z minus x squared minus y squared equal 0. All right, who can tell me what that is in a word or two? Yeah, this is a cone. This is a cone. It's actually a circular cone. It's not even elliptical, it's circular, because this is the same as, easier to see it this way, z equals x squared plus y squared. Okay, and this is a cone. And I'm going to sketch it with CalcPlot 3D. This is the easiest way. And we get x squared plus y squared. Okay. It's not quite a cone, though. You guys thought it was a cone. So I figured I'd show it to you. Why is this not a cone?
It's not flipped along the other axis.
There's a bigger issue. Even if it was, it's still not a cone.
It's not pointed.
Yeah, what do you call this thing? It's not a cone. What do you call it?
A paraboloid?
This is a paraboloid. It's not a cone, it's a paraboloid. A cone would be z squared equals x squared plus y squared. But if it's just z equals x squared plus y squared, it's a paraboloid, right? Or the non-mathematical way of saying it is bowl. So it looks like a bowl. So by the way, this is not the domain. The domain is everything but this. Okay. Any questions? Any questions on this example? Any questions? Yeah, there are times when you have to deal with that. If it were a z squared equals x squared plus y squared, that actually comes up in physics. Anyone know where? Where that's a problem with the domain in the real world. Not your everyday world, but physics real world. That comes up in what's called the light cone for black holes. Okay, I'm not going to get into that, but you can trust me. And those points like don't exist. It's very weird, very bad. Okay, never go into a black hole. Any questions at all on any of this? Okay, as I mentioned, today was our last day of non-calculus. So starting Monday, we actually revisit, we start calculus again because we've had a long break from calculus. We've been doing analytic geometry for a while. And what we're going to be doing starting Monday is we're going to be doing the calculus of multivariable functions. So we're going to be looking at, we're going to start in the same order that you did in Math 105. What was the order you did in Math 105?
And then
First thing was limits, and then?
differentiating techniques.
There was something in between, a calculus word. I know it's been a while. Continuity, do you remember that? What it means to be continuous. And actually the good news is that all happens in just one day. And then after that, we're going to go to derivatives in multivariable functions. We're not going to go to integrals of those. That's next quarter. And then after we're done with that, we're going to go back to limits. And we're going to spend many weeks on just limits. And I will let you know that's hard. So sorry about that. But that's pretty much all I have to say. I'm going to stop my share. I'm going to stop my recording.